So let us continue our discussion. So in the previous lecture, we were looking at the role of conformational flexibility of the ligand. So and the role of pre-organization. So let us now go a bit more into the details of pre-organization of the ligand and its effect on the binding constant in host case complexation behavior. So we look at the just to recapitulate, we look at the porins, which are the open conformation of the ligand, which has the donor atoms positioned, and you can see that this forms the host case complex, and this is operating because of the Chilet effect. In the next case, we have got a close conformation, or we have got a cyclic conformation with the donor atoms positioned here, and then when the guest approaches, we form the metal complex, the host case complex, where the stability comes from the operation of both the Chilet effect as well as the macrocyclic effect. And as we discussed already, that the macrocyclic effect is the additional stability imparted to the system because of the presence of the pre-organized conformation. Why the pre-organized conformation is important? Because there is no energetic penalty paid to actually change the conformation and make it adopt the right conformation for binding. So because that energetic penalty has already been contributed in the process of synthesis of the ligand, the macrocyclic effect becomes operational. And if you now want to enhance the magnitude of the macrocyclic effect, then we can further make a more rigidified host. For example, we can have a bicyclic host which has the same set of donor atoms and has got bicyclic host, in the sense one is this bicyclic, one system cyclic, and this is another cyclic system. And then in the presence of guest, we can have the corresponding macrobicyclic host case complex, and the magnitude of the binding constant was found to increase K3 greater than K2 greater than K1, which reflects the fact that increasing degree of host organization results in enhanced magnitude of the binding constant. Now, so it has now been realized that the delta G0, that is the Gibbs free energy change for the process, assuming that we are doing the experiments at room temperature, that is at 25 degrees centigrade, the magnitude of the binding constant is related to the Gibbs free energy change. More negative is going to be the Gibbs free energy change, higher is going to be the binding constant. And we also know that the Gibbs free energy change comes from the enthalpy change for the process minus the entropic contribution. In the case of the open conformation, there is an entropic penalty, because we have to now, as already discussed, we have to change the conformation of the ligand and bring it into a more rigid structure whereby it loses its degrees of freedom. So thus the entropic term becomes unfavorable, and to offset the unfavorable entropic term, the delta H0 has to be sufficiently large so that the delta G0 for the process is negative. And so this is what leads to, because the delta G0 for the open conformation is lower, we adopt a cyclic conformation where the entropy change for the process is minimum, because there is no entropic penalty now that has been paid again during the time of synthesis, because we have made a cyclic conformation, we have made a closed system. So this unfavorable entropy loss does not take place, and therefore the T delta S0 term is more negative compared to the open conformation, and this results in delta G0 being more negative for the closed system. When I say the closed system, it means the cyclic system, And in order to evaluate these thermodynamic processes, and these quantities, the thermodynamic parameters, have been evaluated in two particular systems. Let us see how the pre-organization of the ligand plays a very important role in complexation with the gas. So let us consider this particular example. And we have methyl, and we have a metal ion Mn plus. Here we also have the same metal ion complexing with, to start with, this is the system A, which is essentially a podent, and we call these cyclic systems here as corents. So this is a cyclic system which we call as corent, and what has been reported is the following. The thermodynamic data reported for these complexes A and B is given here. Log K is equal to 11 and it is 15.3 for the complex B. The delta H0 is minus 44 and this is minus 62, and T delta S0 is minus 20 and this is minus 26. So right away we can see that there is an increase in the value of log K by around 10 to the power 4 times. So here we can see very clearly that the ligand B is pre-organized. So this is the operation of the macrocyclic effect, because the conformation of the ring has already been predefined. It is already a rigid conformation. The donor atoms, as we know that host has got the converging site property, you can see that the donor atoms are converging towards the metal ion and they are already oriented for effective binding with the metal ion. Also we know that if the ligand were open, when the ligand was in the open conformation and we have to now bring it into the closed conformation, for example in the case of the podent, we will have to minimize the lone pair repulsions, and that has to be overcome by favorable metal ligand interactions. So the overall enthalpy contribution comes from the maximization of the metal ligand bonds and the minimization of the unfavorable lone pair repulsions. Now because this thing is more severe in case of podent, this reflects in the delta H0 value being slightly less negative for A compared to that of B, because in case of B already the organization of the ligand is more rigid, it is already pre-organized, the lone pairs are spatially positioned. So overall the unfavorable repulsions have been taken care of. So now it is the maximization because of the lone pair metal binding which dictates the delta H0 term. And from the entropy change also you can see that the T delta S0 term is more negative for B complex, again justifying the favorable entropy which is present in the case of B complex compared to A complex. Here in case of A we have realized that the entropic penalty has to be played during the process of change in conformation of the podent to bind with this particular ligand. So the operation of the cyclic effect and the chelate ring. So you can see here this is one chelate ring, this is another chelate ring, this is another chelate ring, this is another chelate ring. There are two 5-membered chelate rings and there are two 6-membered chelate rings. So two 5-membered rings and two 6-membered rings are operational. Here you have got one 6-membered ring and here you have got two 5-membered rings. So overall the chelate effect is also more in case of B, and the ring being cyclic in nature, the ligand being cyclic in nature, it is pre-organized, therefore the macrocyclic effect also operates. So the extra stability originates from both the greater number of chelate rings as well as the macrocyclic effect, which results in high value of the binding constant for complex B compared to that of the complex A. And this experiment has been done in case of both the metal ions, that is copper ion as well as zinc ion, to demonstrate the role of pre-organization in metal ligand complexation. Now so we have now realized that pre-organization plays a very important role in case of binding. And now we would now like to go and try to explore the next topic in this series, wherein we would like to look at the role of solvents. Role of solvents in host guest complexation behavior. So, this is a very important entity. The solvent is an important chemical entity. In host guest complexation behavior. Now, why is the solvent very important? The solvent is important because it has to stabilize the host and the guest via solute solvent interactions. So, we have got the host molecule, okay, and it has to be solvated by the solvent molecules, such that there are enthalpy changes associated with the process which is negative. Similarly, we can have the guest molecules which has to be solvated by the solvent molecules, such that the enthalpy change for the process is negative. So, the fact that solute solvent interactions are very important because the enthalpy change associated for the process is very negative. And why is the enthalpy change negative? Is because there are different kinds of interactions via hydrogen bonding primarily. By hydrogen bonding primarily, between the host / guest and solvent molecules. We can see that water can form hydrogen bonds with the host molecules. Okay, water can form hydrogen bonds with the host molecules. Chloroform can form hydrogen bonds with, say, a carbonyl group. Say we have got an organic compound which has got a carbonyl group, and we have got chloroform. It can form a CHO hydrogen bond. Similarly, you can have formamide which can form hydrogen bonds with the host molecules. So, these are the polar functionalities. These are the acidic hydrogens which can form hydrogen bonds with the host molecules. So, more is the number of hydrogen bonds, more extensive is going to be the solvation between these polar entities and the donor atoms, which are the electronegative atoms on the host molecule. We can also have interactions between non-polar functionalities, like for example benzene with an organic molecule which is the host, which has got also a pi system. So, we can have favorable interactions between benzene, that is the non-polar part, with the non-polar part of the host. So, you can have these pi stacking interactions between the solvent molecules as well as the host molecule. Now, what is the proof that these solute solvent interactions are present? The proof is that when you will crystallize these host molecules from the solvent, then you will see that the solvent molecules are included in the crystal structure. and as we discussed that you have got voids in the crystal structure where the solvent molecules can now go and get included, and they are actually held by these either the dispersive interactions or the strong hydrogen bonds. So, in large number of cases, for example, when crystallization has been done from water molecules, water has been included in the crystal structure. When the crystallization has been done from other polar molecules like for example methanol, ethanol, propanol, butanol, these polar solvents have also been included in the crystal structure, and they form strong OHO or OH and hydrogen bonds with the host molecules. That means there is a strong hydrogen bonding between the solvent and the host molecule, and when you crystallize it out, because these are favorable on enthalpic grounds, there is enthalpy change negative associated with solid solvent interactions. They tend to get crystallized out and stabilize the crystal structure as well. So, these polar kind of solvents can also interact with the oxygen and the nitrogen donor atoms on the host molecules. We can also have dichloromethane, which is very common, which gets included in the crystal structure. Dimethyl sulfoxide, interestingly CH3 SO CH3, here the sulfonyl group actually accepts hydrogen bonds. So, it accepts hydrogen bonds from the host molecule. So, host molecules need not always have the donor atoms, it can also have the hydrogen bond donors are present on the host molecule. The hydrogen bond donors on the host molecule can interact with the more electronegative oxygen atoms on the solvent, forming NHO hydrogen bonds, and these can lead to inclusion of DMSO in the crystal structure. Same thing we can have for NN dimethyl formamide, HCONH2. You will see that the carbonyl group participates in hydrogen bonds with the NH or the OH groups of the host molecule. So, it is not necessarily always the donor atoms participate, but it can also be the more hydrogen bond donors from the host molecule which interact with the solvent, forming strong hydrogen bonds and therefore getting included in the crystal structure. And it has been observed that large number of structures do have formamide or DMSO included in the crystal structure. Even ethyl acetate is another polar solvent which gets included in the crystal structure, and sometimes hexane is also used with crystallization, because ethyl acetate or DCM are very polar solvents and they tend to evaporate fast. So, hexane is added so as to lower the rate of evaporation of the solvent, and sometimes depending upon the nature of interactions between the host and molecules and the solvent, more than one different kind of solvent can also get included in the crystal structure. So, the crystal structure need not always have a single solvent, it can also have more than one solvent which were used during the process of crystallization. The process of crystallization is such that you need to have the solvents which dissolve the compound, and then crystallization takes place, and there are many other properties of the solvent which play a very important role. For example, in addition to hydrogen bond donor, hydrogen bond acceptor, these are the two fundamental properties we looked at with respect to solvents at the chemical level. At the molecular level, the solvent can have a hydrogen bond donor or it can be a hydrogen bond acceptor, but what is also important further is the dipole moment of the solvent, which is reflecting the fact that how polar my molecule is, dipole moment of the solvent, dielectric constant of the solvent, dielectric constant, surface tension, viscosity, etc. So, some of these properties are very important for solvents as well, and the literature has the values for all these physical properties of different solvents: dipole moment, dielectric constant, surface tension and viscosity, and these also play a very important role in deciding the properties of solid solvent interactions. Now, keeping in mind that solid solvent interactions are very important, we need to look at now that most of the experiments in supramolecular chemistry are going to be done in solution, the role of the solvent becomes very important. And in this regard, what has been proposed is that when you need to keep in mind that, say you have got an organic molecule. An organic molecule has got polar regions as well as non-polar regions. Now, if you add water, it is the polar functional groups which will interact with the water molecules. This is an indication of strong hydrogen bonding. So, this is an indication of hydrophilicity. That means the water molecules interact with the host molecules favorably. However, if the water molecules do not interact with the host molecules favorably, why? Because the host molecules can have non-polar functional groups, then the non-polar functional groups repel the polar functional groups, for example, the hydrogen atoms of the polar molecule, then it is a measure of hydrophobicity. So, hydrophilicity and hydrophobicity are two very important aspects when it comes to considering solute-solvent interactions. Hydrophobicity and hydrophilicity. So, if the interactions between the solvent and the host molecules is favorable, and when you say it is favorable, it essentially means the free energy change of the solvent molecules, which if it were to be hydrophilicity, that means there is favorable interaction between the water molecules and the host molecules, then the free energy change associated with the solvent molecules is going to be negative. If it is negative, that is the free energy change is negative, then it indicates hydrophilicity. But if the free energy change which is associated with the solvent molecules is positive, then it indicates hydrophobicity. And this is something which has been very well realized. For example, if you take leaf and you have these veinlets, and if you take water droplets, then it has been observed that the water droplets will come too close to each other and they will coalesce to form a large droplet of water on the surface of the leaf. Why? Because there are strong unfavorable hydrophobic interactions between the water molecules and the surface of the leaf. So, these interactions are unfavorable because the leaf of the surface is hydrophobic, and the driving force is that the water molecules now interact with each other, form larger droplets because of the favorable hydrophilic interactions between themselves. So, water-water interactions lead to coalescence, and because the overall process is associated with the negative Gibbs free energy change, it is favorable, and the fact that these coalesce together and form larger water droplets is a measure of hydrophilicity, and the fact that these water molecules now repel the leaf surface indicates that non-polar parts always try to be with each other, whereas the polar functionalities always try to be with each other, and this is a reflection of the so-called hydrophobic effect. So, the hydrophobic effect is a proof that in a system when you have polar functional groups and non-polar functional groups, the non-polar functional groups will always try to come close to each other and avoid the polar functional groups, as has been demonstrated in this case, and the polar functional groups will always try to interact with each other, and because of the favorable hydrogen bonds, because of the hydrophilicity associated with the processes, and this phenomena is referred to as the hydrophobic effect. And this is what also is operational in all kinds of biological systems, that is the hydrophobic effect is something which is ubiquitous. Whether you have a biological system or a small molecule systems, always the polar parts try to be with each other, and the non-polar parts try to be together, and this balance between the hydrophilicity and the hydrophobicity is what decides the overall stability of the system. So, a favorable balance between hydrophilicity and hydrophobicity is what decides the overall stability of the system. For example, in terms of the overall Gibbs free energy change associated with the process, wherein the role of solvent is very important, both this hydrophilicity and hydrophobicity decides the overall stability of the system. So, now in the next class we will discuss about more about the role of solvent processes in host case complexation and take up further examples. Thank you.